Alright guys, let's begin. Yesterday I taught you all how to do the calculations, right? Of the equations of alpha decay, beta decay and gamma decay. I hope you all remember that.
Yeah.
Today I'm going to be revising with you guys a quick revision of what are alpha particles, beta particles, gamma ray. I'll also be discussing about the uses and half-life part. Okay, and then we'll solve some questions quickly. Alright? So let's have a quick or let's just read this part. This is all easy part. If you get stuck anywhere, let me know. I'll quickly start off with the half-life part with you guys, okay? Let's make it productive. Just very
Okay.
simple things. See, uses of gamma rays, you all just need to memorize all of this. If you get stuck anywhere, just message me,
Yeah.
I'll help you all out. I'm teaching you all this part now. The formulas
Okay.
for finding activity. The first formula that you'll need to memorize is what? N is equals to given period upon the half-life, where N is the number of half-life. Then the second formula that we would be using is in terms of activity. If they give you any question, like in the question, if they are discussing about any activity of a sample and they ask you what's the half-life of it, then how do you find it? Or if they ask you what's the activity, how do you find that activity? This is the formula for it. It says A is equal to A naught upon 2 to the power n, where A naught is what the original activity that would be provided in the question. N would be the number of half-life that we find out, and we put it as a power of 2, and when we solve this we'll get the activity left after several half-life. Okay, and the same, this is a general formula. Basically they would be just changing the words from activity to atoms, from atoms to count rate. The whole logic is the same for all of them. See, everywhere you would be dividing the original number of activity or the atoms or the count rate by 2 to the power of n, where n would always be the number of half-life. Do you guys get this part? See, only this terminology is changed over here. Like I told you for Avogadro number, like number of particles or atoms or molecules, they all have the same formula. We just keep changing what we are finding. Okay?
Okay.
Any questions in this part? If you all are confused, let me know about this formula.
No.
These.
No,
Okay.
we got it.
Now have a look here. In terms of mass as well, same thing. See, basically what you all need to remember is that they could ask you the activity or the atoms or the count rate or the mass or the volume in the questions. And for all of them, what will you have to do? You will have to simply get the original values that are provided in the question, and you need to divide them by 2 to the power n, where n will always be the number of half-life. Okay?
Okay.
Let's see now. Let's have a look at let's solve some questions. Have a look at this question. One isotope of iridium 194 is represented by this. The isotope decay, this is easy. We did it yesterday. Can you tell me? Okay, we got a beta decay. For beta decay, what does beta represent? An electron, correct?
Yeah.
So if beta represents an electron, what should be I writing over here and over here? Would this be 0?
Yeah.
Yeah. And would this be -1?
Yeah.
Yes. Then, according to this, what would this be then? 194 minus 0 is same. Correct. This will also
Yeah.
be 194. What about the other part?
78.
78. Very good. Let's move on to our next question now. See what are they saying here. The half-life of iridium 194 is what? How much? 19 hours. And a sample of iridium has an initial count rate of 1100 counts per minute. We have the initial count rate, and the half-life of iridium is 19 hours. We got the half-life, we got the initial rate. They're asking us to calculate what? The count rate for the sample after 38 hours. So first of all, I need the number of half-life. Yeah. How do we get the number of half-life? This formula. Always get the value of n first and then use these formulas. Okay.
Okay.
So how do I find the number of half-life? I am given the formula. The formula says we have to divide the given period by the half-life. What's the given period to us? This is the given period. Okay. They are saying calculate the count rate for this sample after 38 hours. So this is my given period. And what is the half-life? The half-life is this, 19 hours. Do you guys get this part?
Yeah.
So what do? I divide what? 38
Yeah.
by 19. What
Yeah.
does this give me? Can you calculate it and let me know? I don't have my
Yeah, hold on.
calculator. If you check the marking scheme, that's why I sent you all the picture. If you check the marking scheme, you see they have done a lot of like a bit of lengthy working over there to get the answer 2 over there. You see there? They've
Yeah.
written 2 half-lives. So I've made it very easy for you. You just need to memorize these two formulas for n
Okay.
and then
Yeah.
just
Okay.
use all of this. Okay. So we
Alright.
got the number of half-life. Our half-life is 2.
2.
Alright, this is the number half-life. Now what do we need to find? The count rate. Okay. What did I teach you for the count rate? See, where's the count rate one? This one. Use
Yeah.
this formula now. What's the original count rate provided? How much is it? See, 110.
Yeah.
So the formula is the count rate is equal to the original count rate upon 2 to the power n. So the original count rate is 1100 over 2, and in the power of n, what do I write? The
2.
number of half-life. Correct?
Yeah.
So 2 2s are 4. This is going to be 1100 over 4. What will be my count rate? Calculate this. Let me know.
275.
275. That's it. This is the answer. Easy.
Okay. Yeah.
So all
Easy.
you have to basically do is just memorize this
Memorize the
formula,
formulas.
and the rest
Yeah.
are same. Whatever they say, they will use the word activity or atom or count rate or mass or volume. Whatever
Yeah.
they do, you just need to get the initial or the original value and divide
Alright.
it by 2 and put the number of half-life in the power of 2. That's it.
Okay.
Okay.
Okay. Yeah.
Let's move on to our next part. State two ways in which gamma emissions differ from beta emissions. So this is all memorization part. Once you all memorize gamma emissions and beta emissions, you will be able to answer them. For example, I did send you all, no, have I sent you all the, yeah, I did send you all the PDF, right? Yeah, this part from here. Memorize everything, the
Yeah.
properties of gamma rays and alpha rays and beta rays, and then just write the answers from here. Okay, I'm not going to do this one. I want you all to do this after you all are done learning nuclear physics.
Yeah. Sure.
Okay, this
Okay.
is very
Okay.
easy memorization part. Okay, let's have a look here. A detector of ionizing radiation measures the background count rate in a classroom where there are no radioactive samples present. Then they are saying that the readings in counts per minute taken over a period of time are shown over here. These are the counts per minute readings. They are saying state two possible sources of this background radiation. Do you remember me teaching you background radiation? See this part, very first part. Where is it? 1 minute. This one here. Do you remember this?
Can you zoom in a bit more?
There you go. Is it visible now?
Yeah. Okay. Yeah.
Right? So over there they're asking us what are the sources of background radiation. You learn all these sources and just give the answer. Okay?
Okay.
So I'll write it here as well in
Yeah.
smaller points, sources of background radiation. Wherever they mention that what could possibly cause background radiation, you write these answers or these points that I'm going to write over here. I'll write 4 to 5 points for you guys. We get background radiation from food or drink. We can get it from the soil or the rocks from the building. We get it from the sun. We get it from medical resources, and we also get it from the air. Okay, so these are
Okay.
all the sources of background radiation. This is what you have to answer over here. Oops, where is it? This part over here. Just write any two reasons over here. You'll get the answer. Okay, now let's start off with this part. Explain why the readings are not the same. What could be a possible reason for that? As they're telling over here that it is taken over a period of time, they haven't taken any time intervals over here. That's the reason.
But wait, can you explain this thing? The
Yeah,
16, 12, 14.
yeah,
I
sure.
don't get it.
See, over here they are getting all the values of the count rates of the radiation that is occurring. Over here the
Okay.
value is 16. Then after a particular time, they again check the
Okay.
reading. Then it was 12. Then after some time they check
Alright.
it was 14. So it's very random basically. Okay, because it is
Okay.
taken
Yeah.
over a period of time. They are not taking these readings over any time interval.
Yeah.
Alright,
Alright.
so this is
Got
what
it.
you're gonna write. If you ever come across any values which are totally different from each other, it means these values were not taken during a particular time interval. These were all random values. These values were taken at random time. Okay,
Okay.
now is this a numerical? Yeah, let's solve this one. With no radioactive sample present, a scientist records the background radiation count of 40 counts per minute. Okay, we got the original count. What is it? 40. Alright, then
Yeah.
he brings the radioactive sample close to the detector. The count rate increases to how much? 200. Okay, so initial was 40. Now how much has it become? 200. Okay, so what's the change in count rate? Can I say it has increased from 40 to 200? So this would mean that 200 minus 40, and this would give me 160. The change in count
Yeah.
rate has 160. It has increased 160 counts per minute, right? So then
Yeah.
after 24 days, the count rate is 50 counts per minute. What's happening here? After a period of time, when they check, they see that the count rate has become 50 counts per minute. Now over here they are saying calculate the half-life of the radioactive sample. We need to find the half-life over here. What could be the half-life here? Look here. In this question, they were asking us the count rate, right? Over here, they're asking us the half-life. How should we do this? You see this difference? This is the difference from what? First it was how much? 200?
Yeah.
And then how? Sorry, first it was
The first 40. Yeah.
40, and then it became what? 200. So I
Yeah.
got one difference over here. This is one difference. Okay.
Okay.
What's the next difference? Then it was 40, and how much it became then? It became 50 after 24
Yeah.
days, right? See
Yeah.
here, it became 50. So what's the difference over here? 50 minus 40. What's the difference?
10.
10. Now we got these two differences. Both of them are what? Both of them are our count rates. The original one was this for me, the change one. And now what's the difference? After from 50 to 40, it is what? 10. So what do? I get these values. What I'm doing here is this part, I'll show you. In the formula, we are getting this value over here. Where is it? We are finding this value over here. Okay. This C naught, the original count rate, is what? 160. Okay. The original count rate over here is 160. C naught over 2 to the power n. Original count rate is 160. This value that you see now of 2 to the power n, this usually basically tells us the current count rate. This was the original count rate, okay, and this is the current count rate. How much is the current count rate? That is 10. Do you get my point?
Yeah.
Okay, so this is basically C, and this one over here is my, not this one, this one is my C naught. So what do I do here? We are not using this. This goes to the left. This becomes 2 to the power n equals to C naught over C. Where I write 160 upon, in place of C I write 10. Okay.
Okay.
So what does this value give me? What is 160 over 10? It's 16. All right.
Yeah.
Okay now. So now if this is 16, what will be the value of n? They're asking me the number of half-life. This. You see this?
Yeah.
This is what I need to find. Now we have done maths. Like you all have given maths exam, right? So
Yeah.
let's do simple maths. 2 to the power n is equal to 16. Can I break it into 2 power of 2?
Yeah.
Yeah, so what would be 16? 2 to the power 4 is 16. Yes or no?
Yeah.
Yes,
Yeah.
16. Yeah. So what do I do simply? I write 2 to the power 16. Now, simple maths. When the bases are same, the powers become equal to each other, right? Sorry, I
Yeah.
wrote 16 here. This needs to be 4. So that means what? That means n is equals to 4. Do you get
Okay.
it? If you don't get it, let me know. I'll do this whole question again.
No, I got it.
Got it? So in this
Yeah.
question, we are using this formula first, and just through this only we are getting the value of n, because they have
Okay.
already given us what? The initial, the original count rate, and the initial one, the present one. And how did we find it? By subtracting these values.
Okay.
All right, now do try to do this one yourself.
Thanks.
I'll solve some more numericals with you guys. Attempt the rest by yourself, okay?
Yeah.
If you all get stuck anyway, then I'll solve this in our next class. Where are some numericals? Again, see, this is also easy, free 2 marks. How do you solve this? Again, beta. Beta means what? 0 over here, minus 1 here. What will this be? 234. And what about this one?
91.
Okay, here they are asking us what? Count rate. Before they were asking us half-life. Now this is exactly like the first question that we solved. What's the count rate provided? See, a pure sample of thorium 234 emits beta particle at a count rate of this. So this is the original count rate, that is 2480. And they have given the half-life as well. See, How much is the half-life? 24 days. Can you see here? The half-life of
Yeah.
thorium is 24 days. This is the half-life. Calculate the count rate for the emission in the sample after 72 days. Now see, this is the half-life and this is another day that they have provided. So again, the same formula, the first one, what was it? N is equals to given period over half-life. What's the given period in this question? The given period is 24 days. Yes or no? See, the half-life
Yeah.
of thorium is this.
Yeah.
No, sorry, I'm so sorry. The given period is 72 days. They are saying we have to find the sample after 72 days have passed. So the given
Okay.
period is
Yeah.
this. And what is the half-life? See, given period upon half-life. So the half-life will be, where is it? This part, the half-life of thorium is 24 days. So I write 24 here. Is my data complete?
Yeah.
So first I find the number of half-life. How do I find the number of half-life? Given period upon half-life. What will it be? 72 over 24. What's the
Yeah.
value of n? 72 over 24 is what?
3.
3. Okay, so the
Yeah.
half-life, the number of half-life is 3. Good. We got n. Now what's the next formula? The count rate is equal to the original count rate over 2 to the power n. What's the count rate provided to us? 2480. Do you get it?
Yeah.
Upon 2 to the power n. What's n? N is
3.
3. 2 to the power 3. Solve this. Let me know what are you getting.
310.
310. Okay,
Yeah.
this is the answer. Counts per second. That's it. Digest this question, guys. Have a look at it. If there's any question, please feel free to ask me. If not, then we'll move forward.
No, I got it.
Got it?
Yeah.
Okay. Let's move on then. Okay, this is an alpha particle. We are getting 4 over here and 2 over here. What should be here? How do I get this value? 235 minus 4, right? And what about this one? 92 minus 2.
2. Yeah.
Let me know the values.
231 and
231
90.
and 90. Good. The rest is all related to the memorization part. I want you all to do it yourself.
Okay.
Okay, here is the numerical part. Thorium produced by the decay A is also radioactive and has a half-life of 26 hours. So the half-life is what? What is the half-life? The half-life is 26 hours. At a certain time, a pure sample washout initially contains atoms. Now look, they're talking in terms of
Yeah.
atoms. So this is the original number of atoms they have provided us. That is 4.8 into 10 to the power 9 atoms. Calculate the number of atoms. That means we have to find A, right? Of the sample that decay in the following 52 hours. That means this is the given period, right? Given
Yeah.
period is how much? 52 hours.
52.
So what do I need to find first? I need to find the number of half-life, right?
Yeah.
Again, number of half-life equals to what? Given period
Given period.
over half-life.
Yeah.
So what's the given period? 52. What's the half-life? 26. Let me know the number of half-life.
2.
2. Okay, the number of half-life is 2. Now what's the next formula? They're talking about atom. Everything is the same. Like I told you, see?
Yeah.
Same. Just put the value of atom and use the same thing. So number of atoms is equals to the original number of atom over 2 to the power n. What's the number of atoms provided? 4.8 into 10 to the power minus 9. Oh, sorry, 9
Yeah.
over 2 to the power 2 because n is 2. Calculate this. Let me know what are you guys getting. Hmm.
0.2 multiplied by 10 to the power 9.
1.2 multiplied by 10 to the power?
10 to the power 9.
You sure?
Yeah.
1 minute, let me check as well.
Yeah.
Yes. Now, okay. Now, one very important thing that I want you all to tell over here. What is this? This is the number of, this is the count rate, okay, that we have found.
I can't hear you.
Can you hear me now?
Yeah.
Okay. So I was saying, this is the number of atoms that we have found. This thing.
Yeah.
Where is it? This one. These are the number of atoms left that we have found, okay?
Yeah.
Where do we go? Here, here. What are they asking us? They are saying, calculate the number of atoms of the sample that decay, okay? Focus
Okay.
over here. They are not asking us to tell the number of atoms that are left. They're asking us for the ones that have decayed. What always, whenever you find all these count rates and atoms and volumes and masses, these all are the ones which are left, which are remaining. Okay?
Yeah.
But in the question, they are asking us to tell the ones which have decayed. So it's very easy. How many were there before? 4.8 into 10 to the power 9. And how many are left now? We just found it. That is 1.2 10 to the power 9. So how many have decayed so far? How do I find it? I subtract the ones which
Okay.
are left from the original ones. Won't I get the ones which were decayed?
Yeah.
Right? So be very vigilant while solving these questions. Make sure
Alright.
that you read it properly. You see how they just change one terminology over here and that changes the
Yeah.
answer as well. So be very careful while solving it. Remember this, that we'll always get the ones which are left. They are asking us in the question the one which is decayed. So subtract it. Let me know what would you get.
3.6 multiplied by 10 to the power 9.
3.6 multiplied by 10 to the power 9. This would be our answer. Okay?
Alright.
Easy.
Okay.
See this question now. They haven't given us anything now. And they have told us that it's a alpha particle emission. Remember I taught you all? Whenever they mention
Yeah.
alpha particle, what do you draw? The helium atom. Right?
Yeah.
So what was
Yeah.
helium? 4 and 2.
Yeah.
So let's do that. Helium atom, or write alpha, or make an alpha particle if you want. Like this. And write 4 here and 2 here. What is it producing? Polium, that is PO. So you write PO. What do I write here? 2 minus 4,
200 and
right?
218.
218, very good. And what about this part? This is 86, this is 2.
Yeah. 84.
84. Okay?
Okay.
Then what do we have next? Okay, another question related to this. So, Radon has a half-life of 3.8 days. So, we got the half-life. Half-life is 3.8 days. At a certain time, a sample contains 6.4 10 to the power 6 radon nuclei. Okay, they've given us the value over here. That is the initial value, right? The initial value is 6.4 10 to the power 6. Calculate the number of particles. That means we have to find n by the radon nuclei in the following 7.6 days. What would be this? My given period. Do you see how I'm finding all the values and the information from the question?
Yeah.
Always make this data first and then attempt solving all these questions, okay? So I have my data. What's the first thing that I need to find? The number of half-life. If I don't have the number of half-life, I cannot find the number of particles that are left, okay?
Okay.
So see, now they're saying emitted. Emitted means the ones which are left. If they would have changed this word from emitted to decayed, I would find the value and then I would subtract it from the original value. Got it?
Yeah.
So let's do this quickly. Let's find the number of half-life first. So where is it? What's the given period? The given period was 7.6 over half-life 3.8. What does this give you? How many half-lives?
Hold on, wait.
The number of half-life is
2.
2. We got the number of half-life. Let's use the next formula. N is equals to what? N naught upon 2 to the power n. What's n naught? 6.4 10 to the power 6 over. What's n? N is 2. So 2 to the power 2. Solve this. Let me know how many particles are left.
Once multiplied by 10 to the power 6.
1.6 multiplied by 10 to the power 6. These are the ones which are left. Okay. And one
Yeah.
more thing,
Okay.
I made a mistake. I'm very sorry. When they use the word decayed or
Yeah.
emitted as well,
Yeah.
okay, whenever they mention the words decayed or emitted, you always do the same thing that we did before earlier. They're not asking us that how many are left, they're saying how many are emitted. Okay, these are the ones which are left. I'm sorry, I was just in a hurry, so I have not kept. So what do we do next? We got the original number. What was the original number? Yes. And
Yeah.
what, how many are left now? 1.6. So how many are emitted or decayed? How do we find it? 6.4 into 10 to the power 6 minus 1.6 into 10 to the power 6. So how many are emitted or decayed? Calculate this. Let me know.
Okay. Wait. 4.8 multiplied by 10 to the power 6.
10 to the power 6. So these are the nuclei, the number of particles, alpha particles that have decayed or emitted. Easy?
Yeah.
Okay.